The aim of this presentation is to describe the ion beam analysis facilities at the University of Surrey Ion Beam Centre. So what is ion beam analysis? Well, it's a collection of techniques that utilise the effects of the interaction of MEV ions with matter. So first of all, we have Rutherford backscattering, which looks at the backscattered ions reflected from the surface. As the ions penetrate the surface, they cause excitation in the electronic system of the target, which in turn causes emission of characteristic X-rays of all the elements that the ion passes on its travels. Other nuclear reactions can occur, which give rise to the emission of gamma rays and other characteristic signals, which can be used to identify specific elements and isotopes. The interaction of the ion beam with the target can also give off characteristic optical emission, which can also be used to analyse the material. The energy loss of transmitted ions can be used to look at the density and elemental fluctuations in thin films. The way in which charge dissipates through a material can also be used to characterise it. MEV ions can also desorb intact molecules from surfaces, and these can be analysed in a mass spectrometer. The target can be tilted so that glancing angle can be used. Using glancing angle and heavy ions, lighter ions can be recalled from the target, and these can also be studied. So what we have is a great combination of techniques which can reveal many things about a sample, and they can all be used, or a lot of them can be used, all simultaneously at the same time with the same ion beam. Here in the Surrey Tandem Laboratory we have a 2 MV tandem accelerator, multiple beam lines. It is equipped with 3 different ion sources, a proton source, an alpha source, and a more general cesium sputter source for heavier ions. There is an implant line to allow implantation up to 10 MeV for heavy ions. This extends our implant energy above that of our 2 MV implanter, but the beam current achievable is significantly lower for most ion species. There is a broad beam chamber where the beam is focused to about 1 millimeter in size. The chamber houses a 6-axis goniometer, that's 3 spatial and 3 angular axes, for sample manipulation and alignment. This enables channeling studies to be performed, which can provide analysis of crystal damage and strain. Coming through the broad beam chamber, the beam can be taken out into air, where it can travel up to 7 centimeters externally and can be focused to a few microns in size. This enables us to analyse samples that may be vacuum sensitive or just too big to fit in the chamber. On the other side of the laboratory is the nanobeam line, in which we can focus the beam down just sub-micron, allowing us to make elemental concentration maps across the sample surface. We also have 2 new beam lines being built, which should be available at the end of 2021. These are a high-resolution PIXI facility and a high-resolution elastic recoil detection system. We also have plans for an additional PIXI/SIM system in the near future. If I continue our walk around the accelerator, we now have the injection magnet just there, going up towards the proton source, and the distance there's the proton source. Here we have the Gatling system, which can be used in conjunction with the IDA equipment, resolution orbitron-sized samples, which can be used for analysing the samples extracted by the Gatling system. Now we're going to look at some case studies. These can be seen on the case studies section of our website, so we won't spend too long on any of these. But what they do is they show the power and flexibility of ion beam analysis and how it can be used across many different fields. So here we're looking at an ion disilicide film that has been made by ion beam mixing of a multi-layer stack of iron and silicon layers. By careful analysis we could see that the argon incorporated into the silicon layer during deposition poisoned the process. Here we're analysing gunshot residue. In particular, we're interested in the trace elements found in the residue, which particularly separate gunshot from other environmental particles and other potential key markers that may differentiate the residue from different gunshot sources. The beauty of a pixie is that as a primary particle is a proton, there's much less Bremsstrahlung background, and we have a much higher sensitivity to trace elements than using more conventional secondary electron microscope EDS systems. So in this study we're looking at a complex 6-device structure which is particularly tricky to analyse. We have to use both RBS and PIXI simultaneously to fully analyse the sample. PIXI provides good elemental sensitivity and RBS provides good depth sensitivity, allowing us to correctly interpret the complex spectra that originate from the measurements. In this study we are looking at a cultural heritage sample, a painting. The painting was bought at auction many years ago, and on the back was written Leonardo da Vinci. Well, you would, wouldn't you? The owner then spent 20 years trying to demonstrate that this was a genuine Leonardo from a lost collection. The Louvre in Paris houses a tandem accelerator with which they do PIXI analysis of paint. They have an extensive database of the trace elements in paint from that particular era. On analysis, we could demonstrate that the painting was from the right era and the right location, and we couldn't prove that Leonardo himself had painted it, but it was certainly a good indication on the way. So in this study we're identifying the metal atoms at the heart of metalloproteins. The technique using micropixie was developed by Jeff Grime and Elspeth Garman at the Surrey Ion Beam Centre. It's difficult to identify the metals in the proteins using conventional X-ray crystallography, and normally the metal is identified by simulation of the protein structure rather than by any direct evidence. In a recent paper, 36 blind protein samples were tested. All the proteins analysed had an entry in the protein databank. In 18 of these, the metal had been misidentified, throwing some doubt on the accuracy of the protein databank with respect to metalloproteins. Okay, well, hopefully we've shown how useful IBA can be and given you some incentive into how it might be used in your own research. Thanks for listening, and hope to see you again one day.